So this sounds very vague. I got it. And let me give you some examples, problems that we are working on. For example, biodiversity. You know, AI to reduce and combat the decline of biodiversity, namely for joint species distributions and wildlife corridors. Bistra worked, and she still does a lot in terms of this area. Another major area is AI to accelerate materials discovery, and in particular for renewable energy. For example, solar fuels. Solar fuels, contrarily to solar panels, you can store solar fuels and use later. So it doesn't depend on the intermittent sunlight. And more recently, I've been working on, actually this problem even relates to ethical AI, because basically, you know, when you study problems, often you emphasize one objective. So we've been looking at, considering this problem, AI to reduce the adverse impacts of the hydropower expansion in the Amazon. So more than 350 dams have been proposed, and obviously dams generate energy, but they can also have tremendous negative impacts and in terms of the ecosystem service. So we've been looking at Pareto optimization to analyze trade-offs of different solutions with respect to different objectives. And I have to say, a lot of these papers, as you see, I tried to put there, have actually appeared in CP, CPAIOR, AAAI, et cetera, But, you know, then I do have also, you know, not only do we have to advance computer science, we also need to really be relevant and significant in terms of other domains. So we always also publish in other domain journals, including, you know, Science and Nature family. So today I will be focusing mainly on these two domains. And in particular, I want to emphasize computational synergies. You know, the importance actually, sometimes when you work across different domains, you get ideas from one domain that you can transfer to the other one. And that's exactly why I'm talking about the boards, even though I really want to talk about the other problem that is really more combinatorial problem that relates to this community. But you will see the synergies. So, you know me, I love, this is my, you know, CP, AI and OR, obviously latent squares. I have studied this problem ad nauseam. And I decided to actually talk about this because, especially for the more junior people, sometimes it's actually good for you to work and focus on simple problems that are easy to understand, and then you dissect and you obsess and you go back to the problem. This has been my problem. So we studied encodings, you know, like CSP, SAT, MIP, packing encoders, and even deep learning encodings. And in fact, I'll talk about that. We studied approximation algorithms based for latent squares, etc. This problem led us to identify this typical case hardness for structured problems, and this was complementing, for example, results in SAT. So understanding the easy, hard, easy behavior in terms of search. Heavy tails, I think several people mentioned, or at least implicitly probably considered heavy tails. We actually discovered heavy tail behavior by studying latent squares. I remember I was watching, you know, this little app that had, a high school student had done, and I fell asleep, and at 4 in the morning, the thing was still running, when typically it would take like, you know, a second to solve. So I thought, there's a bug. I thought it was a bug. No, it was a feature. And based on that, that led us to restarts. You also talked about, a lot of people mentioned restarts, and including imbalancing parallel search, where we actually show that the heavy-tailed explain superlinear speed-ups and algorithm portfolios or ensembles. So we also, believe when we first reported heavy-tailed behavior, there were those who really were so convinced that we were completely wrong that, that was good because we kept working on it and showing formally that backdoors explain the heavy-tailed behavior. Of course, as Aaron mentioned, backdoors are not easy to find, but they actually explain why we have this, why restarts are so effective. We also introduced streamlining reasoning and XOR streamlining with trying to solve spatially balanced latent squares, model counting, Sudokus, Multi-Mixed-Sudoku, I will talk about that, and deep reasoning nets, I will talk about that today, and scheduling and timetabling, a particular case of latent squares. So basically, and also the design of scientific experiments. In fact, this little problem in building spatially balanced latent squares for testing fertilizers was perhaps my first problem concerning computational sustainability. So what's the point that I'm trying to make? I already mentioned it, but sometimes it is actually good for you to work and dissect the problem and really, push it to go deep, which nowadays everybody is into deep learning, but not necessarily deep paper. So that's something we want to try to, avoid. And as I say, ask me about open latent square problems. There are many, and I'm still trying to solve them. But today I really want to talk about, some computational sustainability problems. But from a computer science perspective, I'll talk about this multi-label or multi-target regression learning for joint species distributions. And I also talk about how the same models were adapted to predict quantum mechanical properties of materials. And then I'll talk about deep reasoning nets, really a framework that is for unsupervised learning, combining reasoning and learning to solve complex tasks. And it is motivated by a very challenging problem in material science called the phase mapping problem, inferring crystal structures from the X-ray diffraction patterns. And if there's time, because I have a lot, I will talk about learning and restart strategies combined with deep learning for AI planning. So I'll start with joint species distributions, and I just want to give you a big picture. I'm not going to go very technical, but I really want to give you some key messages. And starting with this problem, a fundamental question in biodiversity research concerns really understanding how species are distributed across landscapes over time. And we have tons of data, lots of sensors, and the best sensor is really the human sensor. And in fact, Cornell has this program, the Cornell Lab of Ornithology has this eBird program. It's a citizen science program that has almost 1 million volunteer birders. They have collected more than 1 billion bird observations. So this is a lot of data. It's noisy data because kids can submit, but it's a lot. So we combine this data with environmental data and using machine learning models, and here you see the output of a machine learning model, we can actually understand, and these models reveal the preference of the species at a very fine resolution. And in fact, these models have been, the lab of Cornell has produced all kinds of models for more than 500 species, and these models actually provide the underlying information for the state of the birds report that actually is produced by, released by the Secretary of State. And these models actually are, allow us to have novel ways of doing bird conservation. And for example, the Nature Conservancy is taking advantage of this information to actually try to protect migratory birds against the drought in California. So based on the models, they allow farmers to submit bids to keep water in the rice fields during the bird migration. So, you know, this is quite cool. And the Nature Conservancy has really, it's interesting, this doesn't show there. Part of the, oh, there's a lag. So the Nature Conservancy has really been able to, you know, rent this extra habitat for the birds, which is much less expensive than, you know, buying land. So, and again, this is only possible because of these exciting new techniques. Well, unfortunately, you know, these models are good, but, you know, ecologists are really, oh, gee. There's a huge lag. And now I understand everybody would mention that. And now I see that. So indeed, you know, the models I mentioned are single species models. But, you know, ecologists are very much aware of the importance of studying the interactions of species. You know, there are all kinds of dependencies, competition, and cooperation. And therefore, it is really important. In fact, I admit that I had to look up the meaning of ecology, and ecology really means understanding the interactions of species with respect to the environment, but also among each other. And so it is really important for them to capture there, and they use this, the theoretical knowledge is that the underlying mechanism is governed by a multivariate Gaussian model. But, and in fact, this is called the multivariate Probit model, which you may be familiar with. However, you know, there are limitations with the current state or the previous state of the MVP models. The features are manually engineered, and normally they can only deal with, you know, 8, 10 features. And really, the big problem is to actually estimate the parameters of the covariance matrix of this multivariate Gaussian model. So let me tell you a bit about this model. So basically now we have M species and locations, and for each location we know what birds we see here. So we have the labels and the environmental features. And as I said, you know, this the ecological prior knowledge is that the species are governed by this multivariate Gaussian model that here I represent by R. And basically, so here we have M dimensions of the species. And basically, a species J is present at location I if the probability of J is greater than 0, otherwise the species is not present. So, well, while computing the marginal likelihood for one species is easy because it's a 1D CDF, computing the joint likelihood is very challenging. And in fact, the current methods such as rejection sampling or importance sampling, they do it sequentially and do not scale up for 500 species. That's what we are trying to deal with. So how can we tackle this problem? Well, you know, it's not the case that all the species interact with each other. So we don't have a click. So we can you know, it's very reasonable to assume a low rank structure of the covariance matrix. And so we can decompose the covariance matrix into two components, T and W. And basically we can then decompose my variable R into T minus W. And then now we can compute the expectation of a condition probability of T given W. So this now is easy to compute. So putting all this together, we actually came up with, the lead author is D Chen, we see there. We developed this end-to-end framework where essentially we have an encoder, you know, we have input the features and the labels, and we have an encoder. This encoder produces an interpretable latent space. And this interpretable latent space is important for us to gather the information for the multivariate Probit, which is the decoder. And in particular, the latent space is going to allow me to compute the preference of the embeddings for the preference of the boards with respect to the environment and the interactions with each other, so the covariance matrix. So this is this structural latent space, and then I have as output my multivariate Probit model. Well, you know, this, we were surprised to see how well this model does. And actually, you know, it outperforms. In fact, we first published this at ICML. We always tend to go first to the CS conferences. And it really outperforms this, you know, the ML models. And in fact, if you normally, ML models use like variation autoencoders, which basically they assume a diagonal matrix, so they don't really compute the covariance matrix. So this outperforms those models, and it also, in fact, we submitted it to a domain, and in fact, I should be talking about that because it's under review. But, you know, in that situation, we were shocked because we got, you know, we were asked to evaluate this again against 144 metrics, and somehow the model survived all these 144 metrics. But anyway, so we really outperform and dramatically, you know, the state of the art in terms of joint species distribution models. What you see here is actually the output of the DMVP for 41 species of wobblers. And so the model can actually jointly model the behavior of over 500 species and really identify species interactions and preference with respect to the environment. And here you see the projection of the embeddings. But, you know, as I don't know if I already mentioned that, but, you know, I always tell the students, we cannot just do this for this little problem. We need to really, you know, show that this applies to other models. And in fact, the ICML paper actually applies this same model to other problems, namely multi-objective detection in computer vision, and also mapping of the Amazon land cover, etc., and you know, outperforming existing models. More exciting, you know, I talked about multi-label classification, but you know, when it comes to species, for example, for understanding fish distributions, you actually want a regression model. So you want a multi-target regression, and you want to estimate abundance. So we actually generalize this model for that. And from there, we actually generalize this model for this density of states predictions for material discovery. And so basically predicting quantum mechanics properties of the materials. And we were quite surprised how well this did. Actually, this paper just came out in Nature Communications. So why am I talking about this model? Because honestly, interesting, it does have more an ML flavor, correct? But, you know, it was so inspirational because for us to keep understand and model the bird interactions, we really had to create this interpretable latent space. And we have been dealing with this problem that I'm going to talk about, this crystal structure phase mapping, for another 10 years. And we had done all kinds of approaches. Actually, Will and probably even remembers that, where we would, you know, because the model has a flavor of, in fact, you know, I tend to go for problems when I know machine learning is not going to work. So that's one of my, I mean, and this problem, as you see, you know, it does have a flavor as a machine learning problem, but then it's, you know, you need to satisfy thermodynamic rules. You know, it is scientific discovery, so you cannot just wing approximate something. No, you need to be quite rigorous. And we had tried all kinds of, in fact, our first paper was submitted to CP, I'll talk about that. And we were kind of stuck and okay, you know, but really not to the point that I will declare now this is really done and we are beating the humans. And what really helped to click was the birds model. I find it, I love this. In fact, we actually wrote a paper. I mean, I was invited to write this perspective to Nature review materials, and exactly about, you know, so it's about computational sustainability meeting material science, how, you know, these synergies. So let me, and one little, you know, what led me to this paper, to this domain, when I started the computational sustainability field or program, I wanted to really do something in energy. And you know, I talked to people, and you know, obviously the good thing could have been the smart grid, but I was, you know, somehow talking to a colleague, he mentioned combinatorial materials discovery. So combinatorial, my little antennas got all excited. And in fact, they refer to this high throughput materials discovery or combinatorial materials discovery. So very simply what, you know, basically they have a silicon wafer, let's say, and they have 3 guns, as you see here, and they spray 3 elements, let's say aluminum, lithium, iron. And so you have this wafer now with the 3 elements. This is like atomic spray painting. So then, you know, that means they can synthesize lots of materials, you know, thousands of materials a day. Typically then these materials are annealed, and then they need to study the materials, and to characterize the materials, they can take, you know, pictures, but obviously it's not, in general, you don't get much, but actually we actually showed you can get some information. I don't know, I'll mention it briefly. You can take hyperspectral data, or you can do, you know, high energy X-ray diffraction pattern, X-ray diffraction, and we have a synchrotron at Cornell. So, and in fact, here is Ron at the synchrotron. I don't know if you know, Ron did a PhD with me, and he was a big CP fan. Now he's at the Polar Institute. So what is the challenge? The challenge is, given the X-ray diffraction patterns, I want to infer the crystal structures. And this is a bit like James Watson went for the DNA. You know, you want to infer the crystal structure based on your X-rays. And this task is very hard, especially in materials, because 2 crystal phases can overlap and mix up. So, you know, while they can synthesize lots of materials a day and characterize lots of materials a day, they cannot really interpret that many. They can only do a few a year. So it's a very challenging problem. CP 2010, we actually, you know, characterize this, formally define the problem and formally analyze the complexity. In fact, if you see you can sample all the pure phases, you actually can solve this in linear time, in polynomial time without noise. But that doesn't happen really. So what is the problem? So here you have a representation of what we call a ternary representation of the wafer with 3 elements: aluminum, iron, silicon, excuse me. And you take X-ray diffraction images, and here they are already integrated. And based on these samples, you want to identify M phases, K pure phases, and some mixed phases. So you can almost think of this problem as a clustering problem. You want to cluster the points into phases corresponding to pure regions or mixed regions, but you also want to have exhibit what the pattern is, what the X-ray pattern is. Well, this would be great, but luckily, physicists know what they are doing. So there are some rules here. This is not, you can produce an arbitrary solution or clustering. There are rules that say, for example, the phases are connected components. There are rules saying if you have 3 materials, you can explain a phase with at most 3 crystal structures, so it's a cardinality constraint. Then you have logical constraints that tell you something like, oh, if they're shifting, which means that you see, alloying, which means the patterns are shifting. In fact, you see here shifting, then you lose a degree of freedom. So there are all these constraints that make this problem complicated, and that's what I liked about it. And therefore, the state of the art, really, machine learning couldn't solve this problem. Another perspective here, you see here, we have a point. This is a pure phase. This is the spectrogram, the diffraction pattern when integrated gives this pattern. This is a pure phase. This is another pure phase. And you see here, you have a mixed phase. This phase is going to be demixed into these 2 phases. And we have the thermodynamic rules. Well, it's not easy to get these papers through computer science, as you imagine me explaining this. And again, my rule is we should not just do things that are just for this particular problem. So, in fact, we actually, when we developed the reasoning nets, I admit it was completely motivated by this problem. But when the time came to write a paper, I told Dee, we need to come up with another problem. And I suggested this problem, that is, you have, 2 overlapping Sudokus that have been solved, and now you need to demix them. You see, it's another demixing problem. And actually, Dee said, Carla, we are so lucky that, we can put together these problems. And I said, no, I've been thinking about latent squares and Sudokus for so long that it's serendipity, and a word that I love. So you see, now I have another demixing problem, but there are others. For example, we actually also have studied detecting elephant calls or flight calls in audio, and that is also a demixing problem. You have a signal, an audio signal, and you want to separate the birds and the bees and the elephants, etc. Or, another example that is like music. If you want to actually identify the instruments, that is also a source separation problem. So, well, this is all nice. However, we have 0 labeled data, no labeled data. We have data, but not labeled data. We have X-ray diffraction patterns, but no labeled data at all. And, the standard methods use them basically because you can think of this problem as, extracting the factors. Matrix factorization techniques do not capture the underlying physics of the problem. And so our strategy is really to integrate machine learning techniques with symbolic AI to tackle this problem. So let me talk about deep reasoning nets. Deep reasoning nets was truly motivated by this problem. You know, that we actually came up with this framework to solve this problem, but I'm going to really explain it using this other problem because it's much easier for you to relate to it. And the way I'm going to do this is, here is a table with symbols. And my question is, can you make sense of those symbols? You know, you see some letters, maybe some numbers, but it's really difficult to see what they are, correct? But what if I give you some prior knowledge? I'm going to tell you that this is actually the two overlapping Sudokus, one using digits from 1 to 9, and the other one using letters from A to I. And I give you the Soduku rules in case you don't know. Everybody should know that. No, you cannot repeat the symbol in a row, column, or block. So maybe now, but it's still very hard for a human to do this. Well, deep reasoning nets actually, by combining, you know, deep learning with reasoning about prior knowledge, namely the Soduku rules, without any label data, can actually demix this overlapping Sudokus into this one on digits and one on letters. And, you know, here is the overall framework that you may, and I'll show you soon. It's actually very similar to the same framework we used for the boards. You know, we have an encoder and we have a decoder. We don't have label data though, but we do have an interpretable latent space. And this interpretable latent space is key for us to keep the probabilities of, to reason about probabilities of digits and to encode the Soduku rules. And the decoder is now conditional gap. So let me show you, just for you to see, you know, very similar to the other structure. And I will tell you what really clicked was this idea of an interpretable latent space. We had done things like matrix factorization, interleaving with, in fact, we had a CP paper with little MIPS to fix the rules, etc. But it was quite, it was not satisfactory because we could not reason about the rules or what's known about, in this case, the digits, or, you know, some notion about digits or crystal structures in the real case. So here we detail there, you know, you see the latent space. Again, it has two parts, you know, one part keeps the probability of the possible digits for each of the overlapping Sudokus, and then it has the shape embeddings for the decoder. So we compare this, let me, you know, more formally, obviously, you know, in the end, we are always solving some kind of formula, correct? So basically, in fact, I call these problems data-driven constraint optimization problems. And the reason why, in fact, one reviewer, when we submitted this paper to Nature, they asked us to actually, why isn't this just pure optimization? And I love that question because I actually had mentioned this to Dee, that this is not standard optimization, but why not? And I'll explain this in a minute. So, but basically, you know, essentially we want to generate the demix patterns. So we have a generator that works on these embeddings such that we minimize the reconstruction of the initial patterns, correct? But now we want to make sure that we satisfy the Soduku rules. And what do we do? Well, if we want to use deep learning machinery, we cannot have a constraint optimization problem, correct? But that's easy. We use a Lagrangian and move this to the objective function. And obviously there's another problem that the constraints are combinatorial constraints, so we need to somehow relax that, but that's also no big deal. We can use entropy-based functions to actually capture the different constraints. For example, if I want to say that I cannot repeat a symbol in a row, I want to maximize the entropy. So with entropy-based functions, you can very easily capture these constraints. So, well, we compare this, there are no unsupervised methods, so we have to compare with the supervised methods, and in particular, ResNet and CapsuleNet, but they are supervised methods, and they do very well in terms of digit accuracy, but because they still are not perfect, they don't do very well in terms of Sudoku accuracy, where we actually do very well in terms of digit and Sudoku accuracy. And then we actually did ablation studies where we removed the reasoning module, where now it doesn't know anything about the Sudoku rules. And you see that the digit accuracy decreases and the Sudoku accuracy goes down the drain. So, and then the same if we remove the conditional GAN, we also have very low accuracy. I realize time is flying, so let me now show the ablation study where we actually show that why this is different from a pure optimization problem. Because so the question is, do we actually learn something across instances? And so what we did was, if we would solve one instance at a time, the accuracy was really miserable. And so we need to get to high accuracy, we need about 100 instances. But these are unlabeled instances, but we still need 100 instances to learn across the instances. Does it make sense? So that's why there's actually, the network is learning the parameters across the instances. And that's why we call this data-driven constraint optimization. And actually, I think there were, I remember seeing some papers at CP, and I think they make a similar point. So that was nice. Let me very briefly say that, a harder problem is completing, demixing and completing. Here, now we have missing cells. So not only do we have to do the demixing task, we now have to complete. So this is a good challenge for you guys, because this is far from solved. This is a more challenging problem. I will not go into details. Basically, we do clear DRNets, where basically we enhance the reasoning module with the LSTM and coupled with the constraint graph, so that the network can actually learn the constraints and generalizes much better. And also we do curriculum learning with restart to really boost performance. Here we show the results. Clear DRNets actually does better than pure DRNets, but you see when we can solve demix and complete up to when we have 25 hints. But now when we only have a few, then it becomes very, for 18 or 17, that's, for the Sudoku, we can't really do much. And even here, we already perform poorly. So let me now briefly talk about the real problem, that we actually wanted to solve. So here is the instance, this problem you know, my colleagues, the material science, had tried to, you know, solve this for over a year to decipher this, to solve this bismuth copper vanadium oxide system. So we have 307 unlabeled X-ray diffraction patterns. So that means each one may be a mixture of 1 or 2 or 3 phases, but we don't know. In the Soduku, we knew there were 2 overlapping Sudokus. Here, we have no idea. So we have this information. We have the information of what other phases have been identified for systems involving bismuth, copper, or vanadium, but we don't know. But, you know, these phases have been identified, but, you know, it's not necessarily the case given the annealing conditions that you'll find them here. But these are almost, you know, abstract phases. They are pure, assuming no noise. So in fact, they are called stick patterns. And in general, we don't see pure phases. We see all these pure spectrograms. We see noisy data. And we have the rules, thermodynamic rules, as I explained before. Well, you know, again, deep reasoning nets actually can identify 19 phase fields. And you see some of the phases are mixtures of 3 phases, some of the phase fields like 3 crystal structures or 2 or etc. And not only does it identify the regions, then it can actually separate and it can actually demix them and identify 13 pure phases. And in fact, additional experiments done by the materials scientists, they actually identified that one of these materials was a good material for solar fuels. So again, you know, you see the structure is very similar to the Soduku, Sudoku deep reasoning nets, but obviously, you know, different. The encoder is actually also multi-layer perceptron, and we are actually in the meantime have replaced with the graph neural network. It produces an interpretable latent space, and this was really the key, because this interpretable latent space is going to allow us to reason about the thermodynamic rules, but also reason about the known phases to see. Because before we would do a matrix factorization, extract the factors, and then look at what's known. Now we can actually extract the factors, but combining prior knowledge of what's known to see if indeed it is one of the existing crystal structures. And, you know, again, here you have the parallel between deep reasoning nets and deep reasoning nets for the multi-Mixed Sudoku and for crystal phase mapping. And you see a key component is indeed, we have these 2 structure latent space to keep track of probabilities of phases, and also the information to generate the patterns or the crystal phases. In this case, the decoder is a GMM, a Gaussian mixture model, because you see the patterns really are mixtures of Gaussians. And, you know, we actually have a data set that is synthetically generated, so we know the ground truth. And in this data set, previous approaches, including our own approach, were far from perfect. And you see here, in fact, DRNets, this is the ground truth. DRNets, you know, we do show the log of the reconstruction loss. It's nice and green. IFD is this interleaved agile factor decomposition. We actually, I think we had a CP paper on that, which basically we interleave the matrix factorization with MIPS, etc., to fix the rules, but you know, it's not perfect, and this is what is used by the material science community that's even less perfect. And here we show metrics for the aluminum lithium iron system, for which we have this ground truth, and you see the accuracy is very good. I have to say this system is also easier. It has lots of phases and actually a lot of shifting, so it's quite complex, but no noise. So, you know, so it's easier in that sense. And we do very well there. For the real system that had never been solved before, we don't have ground truth, so we cannot talk about accuracy, but the loss is decent. And then we have all kinds of metrics to see how our factors approximate or how close they are, the phases, the crystal structures that we discover, how well they match existing ones, and the phase fidelity is very good. And, you know, and we satisfy pretty much all the constraints, while our previous system also, because we were, you know, forcing with these MIPS, etc. But by satisfying the constraints, we were increasing the loss. And this system violates constraints, and also the loss is not very good. Again, here we show that for the one where we have synthetic data, that we need at least 150 X-ray patterns to be able to reach high accuracy. Again, we don't have any labeled data. It's all about supervision by reasoning. That's because we don't have labeled data. So, just an aside, we have a much bigger project, you know, SARA. SARA stands for Scientific Autonomous Reasoning Agent. I always like giving female names to my little robots. They are actually not mine, to be honest. This is all, I mean, for you to do this research, you really need to team up with material science. You know, these little, you see a depiction of SARA controlling these laser spike annealing, and you see the profile of the laser. And here we actually have shown, and we have this paper with Sebastian on the period in Science Advances, where we show that actually we can use RGB data to give us a rough idea of the phases, and then hyperspectral data that allows better to us to understand, you know, identify the phases a little better, and then X-ray diffraction patterns to really characterize the phases. And so we actually have done experiments and using active learning to control the synchrotron, where they actually had the laser spike annealing inside the hatch with the X-rays, the beam. So that was quite something. It was big news at Cornell, and it was very exciting. And basically, you know, the vision is that, you know, SARA really encapsulates or will encapsulate the scientific method, ranging from formulation hypothesis, planning and executing experiments, interpreting the experiments, and producing new knowledge. And here we already see how SARA is doing active learning. I'm not really going to talk about it, but that was quite, it is, I have to say, this system is much simpler than the one I talked about. It's just a bismuth oxide, and you see the phases produced by SARA. So again, you know, I stress that we always start by publishing, you know, CS conferences, but then we really, you know, I always want to make sure that we, and obviously my colleagues, they all want to, in fact, they want to always publish in, you know, the material science journals, or, you know, Nature or Science Family. So now, skip.
Okay. Yeah, I think it might be.
So ask me about curriculum learning and restarts for boosting during your questions. And basically, I'll go straight to, essentially, actually, I can tell you the punchline is that we were quite surprised to see that if you combine some deep reinforcement learning, kind of, actually we use a star with deep learning policy and the value network, you can actually beat the customized solvers for Sokoban, which is a very interesting AI planning problem. And we were surprised. And the punchline is that if you look at the trees produced by the algorithm, they are super skinny. The successful runs, we use curriculum learning and restarts, and the successful runs are really, really skinny. And what the student really, I mean, this was massive experimentation, discover is heavy tail behavior, but everybody has, and as far as I know, nobody has really shown heavy tail behavior on the left-hand side of the tail. There has been tons of work, myself, students, planning, I know a lot of people with showing heavy tail behavior on the right-hand side. So meaning that you can have very short runs, but now and then long runs. But we actually show that these instances are inherently hard. So on average, they take exponential time, but you can find very, very short runs. And, you know, I had conjecture that, but frankly, I never really believed in that because, but yeah, this was the exciting part. And so let me wrap up because I don't want Vista to be unhappy with me. So the conclusion is that, you know, pure data-driven AI ML is really not suitable for scientific discovery. And instead, we need to use a data and knowledge-driven AI ML approach, basically combining data-driven with knowledge reasoning. I admit in my career, I underestimated the value of the data. I'm now realizing you can get a lot out of the data. There's a lot of signals out there. So it is really important to combine a data-driven approach with knowledge reasoning so that we can reason from first principles as it's done in scientific discovery, and we can factor in prior knowledge. We can reason about uncertainty, for example, for active learning, and obviously that allows us to deal with combinatorial spaces. I show that, you know, a good strategy is, for example, to couple, to have interpretable latent space in deep learning to encode prior knowledge. And I didn't show, but kind of mentioned briefly how curriculum learning and search and restarts plus deep nets or a policy value network can really be effective to tackle very challenging problems. Okay, and thank you. This is actually a subway line of different projects, computational sustainability projects. I talked about, and the lines are computational themes. I talked about this pattern remixing. I talked a little bit also about the prediction for bird conservation and materials. And thank you.
We have some time for questions.
Hey, Peter.
Just what are these interpretable latent spaces? I'm just fascinated what they are. Can you tell us what it is, for example, Sudoku splitting?
What it is?
Yeah.
It's literally you keep track of, you know, the probability, units, 2 units to keep track of the probabilities of the digits. So for each Soduku, you have 9 digits, so you are going to have 18 to keep track of those probabilities, and then the same to keep track of the embeddings. That's it. And then, but then you see now, because you have units that say the probability of a 1 or 2 or whatever, now you can encode constraints. So it's really, you know, thinking a priori, you know, it's like you know, when you are teaching how to encode a problem, you know, often the students think about, oh, what's my objective? I only have, I need variables for the objective function. Well, here we are telling you, no, you also need variables for the constraints. And that's what you are going to put. Your interpretable latent space is going to have variables to represent probabilities or represent embeddings that are going to collect the information that you pass to the generator, because the generator has to generate an image. So you want to create an embedding for a 9. So then your conditional, then you say generate a label, an image for a 9. So for the materials, it's very similar. You know, again, we keep track of the probabilities of the different phases, and then information for the Gaussian mixture model to generate the patterns, the you know, known patterns. So, but I'm happy to give you more details. So,
Carla, 2 questions. One is that you said this wasn't an optimization problem, but after you finish all that stuff, is it possible to transform it back into a new optimization problem? So that's question 1. Question 2 was that you mentioned errors. So I wasn't sure whether you meant errors was like because of the mixing of phases or those are experimental errors.
I mentioned errors.
For the base stuff. For the material science, also noise.
Oh,
okay. So that the reason why I asked that is that, you know, with constraints, right, it may be difficult to reason about noise.
Yeah, and
because noise is like, what does this mean?
I'll start with that question. I mean, it is noise, you know, taking measurements.
So it's experimental noise.
It is experimental noise. And in fact, that's how we realized an SMT-based, because we tried an SMT-based approach, assuming we only need the position for the peaks. But there was so much noise that, you know, we couldn't really use such an approach. So that's what we really had to give in and really say, no, this, we need to do some kind of machine learning approach, and then we start doing matrix factorization. But then we were not able to you know, constrain the factors produced by a matrix, no negative matrix factorization. So think of SVD, but now you need to impose that the factors have to be positive, and that's NP hard. And now if you need to constrain the factors to follow these rules, we don't really know how to do that. But not only do you want to constrain the factors to follow the rules or the thermodynamic rules or the Soduku rules, we want them to look not arbitrary things that can even pad the noise. You want them to look like plausible crystal structures. So we actually were not using information about known crystal structures that, in fact, for the Bismuth copper vanadium oxide system, we went to our collaborators, we discovered 16 new phases, and they said, are you smoking? I mean, no way. So it was false, 16 new phases. Exactly, because basically, you know, the doing some kind of non-negative matrix factorization, there's an incentive to pad the factors with the extra thing to decrease the loss, the error. So those were not real factors. Now we condition, this to adhere to the known phases, and that's why we have this part, which is very important. You see, here we have this mixture, the Gaussian mixture model that is basically telling me, well, in principle, it should look like what's now. And that is really how we bring prior knowledge. Your other question is very good. And I like it that because I asked that question myself. You know, why don't we just use, stochastic gradient, put everything together? And that's exactly the point that I was trying to make. If you are going to solve, let's say, demix a Soduku, one at a time, you can actually, it doesn't work, even for this setting. You really need to have at least 100 instances to learn the parameters across the instances. And of course, you can now, build the network and work on 100 instances and transform this into an optimization problem. that would work. But really, you'd need to use the learning across the instances, and that's true for the Soduku, and it is actually also true for the X-ray diffraction patterns. And in fact, the material science, the way they do it is exactly one at a time. And we actually have shown that, you know, that is truly suboptimal, because you need to have, because, you know, this problem is in principle not invertible. You can, given an X-ray diffraction pattern, there are many ways to decompose this mixture. So you need to constrain it to actually have meaningful solutions. And if you just do one at a time, you actually have not very accurate solutions.
So in the interest of time, let's take Carla again.